All right, so let me start by thanking Manas Kulkarni and the organizers for inviting me here to this new wonderful center for theoretical physics and theoretical sciences. It's a great pleasure to be here, and I've already had a number of really interesting exchanges. And so today and tomorrow I'd like to tell you more about spin qubits. For those of you who have been here last week, and have enjoyed Jason Pera's lectures, some of this will sound familiar, but I'm going to highlight it more from a theory perspective. But of course, I'm going to show also some experiments and some correspondence between theory and experiment. Okay, so let me start. Basically, I want to tell you what this is about and how maybe it fits into the broader context of this workshop. So what I'm talking about mostly is single spins as a controllable open quantum system. So basically that's what qubits are, and in my case the qubits are spins. So for basically all of this, when I say spin, I mean the spin of a subatomic particle, usually an electron, or maybe a few electrons, or atomic nuclei. Right? And so then some of these spins, the electron has spin 1/2, some atomic nuclei also have spin 1/2, some atomic nuclei have higher spins. If you have a spin 1/2, that's already basically an ideal quantum bit, right? Because it has two distinguishable states, spin up and spin down in some basis that you can choose. And you can identify these two directly with your logical basis, 0 and 1, that you need for quantum information processing. So that's an ideal qubit. That's the connection between spins and qubits. In some sense, it's also the smallest possible quantum system that you can think of because it has only 2 levels. So in some sense, this is also a nice playground to understand maybe things that you want to explore for more complicated objects later on. So it's not only, maybe I'm not only thinking about applications here, but also about understanding fundamental concepts in quantum physics, which we would try and find out using the example of these 2-level systems. Okay, so then basically, if you want to use, let's say, the spin of electrons, and I'm talking here about solid-state systems, then of course you could think electrons are of course everywhere. You could take a metal, and then there are a lot of free electrons, but the problem is these electrons are mobile. They're just moving around very quickly, and if you have one spin and you do something to it, then a short time afterwards it's going to be gone and lost in a sea of billions of electrons, and so that's probably not what you want if you want to study the dynamics of a single spin. And so what we're talking about is systems where you can address very precisely only few spins, few electrons that are well localized, so you can find them when you have done something to them, you can find them later on in the same place. So we're talking here mostly about localized electron spins. And there's a variety of systems where spins, electrons can be localized in solid state. One example is semiconductor quantum dots, and I'm going to talk more about those. Another example is defects in wide bandgap semiconductors such as diamond, which are occurring naturally. There you also have electronic spin, which is very well localized. And yeah, I think I've already alluded to it. These spins are open quantum systems. They're embedded in a solid-state matrix, and they're talking to other degrees of freedom of our system. And in some sense, that's good because we want to control them. But of course, it's also unavoidable that we have uncontrolled interactions with the environment. And therefore, we have to somehow understand this, the effect that this interaction with the environment has on our system. So maybe just as a broad overview, what kinds of degrees of freedom or interactions you can imagine. Definitely these spins have a magnetic moment, so they will be interacting with magnetic fields. And of course, that's one way you can control spins. And we've heard, for instance, by Patrice yesterday that you can do magnetic resonance, and so this is something you can use. But of course, there could also be some magnetic field fluctuations that you do not control, and then these will probably dephase or have some bad effect on your spin. Another possibility is that you have other spins around that maybe you don't want to be there or you don't control, and these can also interact with your spin via their magnetic moment. And this is also something that has caused some trouble for spin qubits in solid state. Then, okay, maybe less obvious, also fluctuating electric fields can have an effect, and I will come back to that later. Of course, the spin of an electron does not have an electric dipole intrinsically, at least as far as we know. But there are many ways the spin can be coupled to an electric dipole. For instance, spin-orbit coupling can do this, or magnetic field gradients can do this. And there are many ways in which, in the end, fluctuating electric fields, which are, of course, also very common in solid-state devices, will affect our spin. Basically, it's also a goal. One of the, I would say, current activities is to use electric fields to control spin. And when you do that, you actually, on purpose, endow your spin with an electric dipole, and then you will also open it to electric field fluctuations automatically. So this is something we should take into account. Then another source of fluctuating electric fields, in some sense, is phonons. So if your spin is sitting in a lattice in solid state, there will be lattice fluctuations or lattice vibrations, and these phonons can couple to the spin via spin-orbit coupling, for instance, and they will have an effect. And okay, there could be other things. I don't know. We'll see. Okay, so this was just basically a short outline of what these lectures are going to be about. And here's a plan of what I would like to do in these 3 lectures. This morning, I'd like to give you an introduction into spin qubits in general, and for those of you who are new to the field, give you some context. And of course, if you have heard Jason's talk last week, then maybe many of this will be familiar. Maybe some things won't. Okay, so this will be the introduction. And then this afternoon, I'd like to talk a little bit more about spin qubits in more unconventional materials, 2D materials. We're looking at a lot of materials that have interesting band structures that basically have an effect on the spin physics and spin dynamics. And this is something I'd like to highlight this afternoon. And finally, tomorrow, I'd like to come back to this point that I was just making, that it would be interesting or very, very convenient to use electric fields rather than magnetic fields to control spins of electrons. And also maybe use a couple spins to the electric field of microwave cavities and so on. So this is a very current development, and I'd like to go into that a little bit more in the lecture tomorrow. So I've definitely made a very ambitious plan, and I'm almost sure that I won't cover everything I was going to cover, but so basically I will just see how far we get and then skip some material if necessary. So for me, it's important that we can go at a pace where you can also ask questions. So please feel free to ask questions anytime during the talk. I'm happy to spend more time on one question and then skip something else. All right. Okay, so let's go to spin. So this is now a very brief primer, and for most of you, this is just repetition or some reminder. So spin is, what is spin? So spin is something, well, at least intuitively, spin is something that's rotating, right? So classically, a spin is something that's spinning, that's rotating. And here's a spin, it's a top. And there is 2 gentlemen are looking at it. Maybe one of them, so it's a classic spin. Maybe one of them is already thinking about quantizing it. And so since this is a lecture, I'm going to give you homework. So your homework is going to be to find out who these 2 gentlemen are. And maybe so the more difficult homework is to find out at what occasion they're playing with tops. So, okay, what is spin? So although I'm a theorist, I can show you an experiment that I have not done myself. But if you put something that contains sodium into a flame, then you will get this yellow color. I think you can put rock salt or kitchen salt and in a flame, and then you will see a yellow color. And if you if you make spectroscopy on this, you will see that it's basically really monochromatic color, and this is the sodium D line, so-called sodium D line. This was labeled by Fraunhofer, I think. And if you look closely, if you have a very good spectrometer, then you will see that actually these are two lines. And now, if you remember in atomic spectroscopy, if you have some kind of, if you already have some sort of semi-quantum model for your atom, you know that there can be these degenerate lines, and they usually come from angular momentum quantization, but they usually occur in either single lines or three lines for angular momentum 1 or 5 lines, so it's always an odd number. But here you have an even number, and this puzzled people. This was maybe 90 years ago, when people were very puzzled about this fact that you can have this, I think what they call this anomalous Zeeman effect. So you have only two lines, and so the one person who thought about this was Wolfgang Pauli, and he wrote, and it's actually interesting to see how sort of confused people were, or basically they knew that there was this, somehow this must be some kind of, so Pauli thought this must be some kind of two-level system, but he had no idea what it was. So you can, from reading this, so I translated this, so from reading this you find that he just uses very contorted language, that this doublet structure of this sodium atom, and then there's some violation of Larmor's theorem. This must be due to some peculiar non-classical two-valuedness of the quantum theoretical properties of the outer electron. So he didn't know that this is spin. Actually, he didn't believe it when people first said it was spin. And so he just said, okay, it's some two-level system, it's quantum mechanical and so on. And of course, he used these many words, and nowadays we have a much more efficient way of saying this. It's just a qubit, right? So it's a qubit, two-level system, quantum mechanical. So he didn't know this yet. Okay, so actually just to finish up this, or kind of complete this historical note, the person who actually speculated that this was had to do with an angular momentum was Ralph Kronig. So he speculated that there was this intrinsic angular momentum that had nothing to do with orbital motion. And he proposed in January 1925 that this was the case. And actually, Pauli didn't like it. Pauli hated the idea, and also Heisenberg. Must be tough for Kronig. So then, in the same year, actually, the spin was really, it was really found that this is a spin. You can put this in a magnetic field, and basically, in the end, it was also Pauli had to admit that this was a spin. So basically this two-valued quantum degree of freedom has to do with an intrinsic angular momentum of the electron. Okay, it's just one more thing that Pauli did, which we will use in this lecture, is the exclusion principle. And basically, and this is just a reminder, I'm sure everybody knows this, but just to repeat. So two fermions, for instance, electrons, cannot occupy the same quantum state. So if you have some system with discrete levels, it could be an atom, could be a quantum dot in solid state, you cannot put two electrons with the same spin into the same quantum level. You can't put two electrons with opposite spin into the same level, or you can put two electrons with the same spin into two different levels. And this was then basically, together with this fact that the electron has this spin degree of freedom, this was then allowed then people like Pauli to explain atomic spectra and the periodic table of elements in the end. But for us, actually, this exclusion principle is also important for many operations that we want to do with spin qubits. So for instance, when you read out single spins, it's very hard to measure the magnetic moment of a single spin. Now, we've heard yesterday from Patrice Berthet that, okay, you can read out, conventionally what people do in magnetically detected spin resonance is maybe they measure 10 to the 10 or 10 to the 13 electron spins, and so that's conventionally done. But if you want to read out just one, that's very hard. I would say nowadays it's not possible with magnetic detection, but you can do something else. You can convert this magnetic information into a charge information. And for this you can use basically this Pauli principle. You by trying to put two electrons into the same state, you can find out whether they're the same way, they look the same way or opposite. And if one of the spin is known, then you can measure the other spin. And this is basically called spin to charge conversion. and the charge can then be read out fairly efficiently. The exclusion principle is also the basis of the interaction that we want to use for spin qubits, so the interaction between spins that we want to use to make quantum gates, so-called exchange interaction, also for initialization and also measurement of entanglement. I'm not going to talk about that. So this is just a conceptual thing that that's quite important. Okay, any questions so far? Okay, this was now very elementary, I suppose. So now maybe let me go back and look at the spin now as a qubit. So what is a qubit? Why do we need qubits? So that, of course, the ultimate goal or motivation is to do quantum computing where you have some classical input, let's say a large number, you have some quantum box here, and you solve some difficult problem, for instance, finding the prime factors of this. This is what the Shor algorithm is doing. But what I'm interested in here is more, it's not what it's doing, but how it works. So if you look inside, we have a way of depicting the workings of such a quantum computer using so-called quantum circuits or quantum circuit model. And this is what it looks like. Essentially, it's a space-time diagram of what happens to the qubits. So these lines here, these depict the qubits, and I've already told you that we want to localize the qubits so we can find them later. And so that's why these lines are horizontal. So the qubits, they put in space, and they propagate in time from left to right. And then there's some events happening. These events is what we're doing to the qubits in order to make a computation. And the events that we want are 1-qubit gates, so where you rotate a single qubit or spin, and 2-qubit gates which act on 2 qubits. And there's a statement in quantum information theory that says that once you have all this, you can do arbitrary computations in principle. So this is very convenient. So now we don't have to think about how to make the entire box, but we can think about how to make these elements. And then basically that's what I'm going to be talking about. Maybe to also put this more into perspective, of course there are many different realizations nowadays of qubits, and I've just listed here 3 that I think are very promising or very successful in making demonstrations. The first is atoms in ion traps, where you use some atomic levels. One picture from Innsbruck. There are many groups that are working on this, and this is a very advanced field where people can manipulate more than 10 qubits, and so this is quite advanced. The other 2 examples are from solid state, and we've heard already about superconducting qubits yesterday in the talk by Michel Divoret, for instance. And so this is maybe one of the most advanced fields where people are making now several qubits and couple them, and several groups and companies are working on the superconducting qubits. So I'm not going to talk about those here. I will talk about electron spins in solids, and I already mentioned that there's basically this semiconductor quantum dot realization here, where you use a semiconductor heterostructure with a 2-dimensional electron gas, and then these gates that deplete the electron gas underneath and leave these puddles of electrons. So here's just a sketch, and this is a scanning electron micrograph from the top of such a structure. So that what you see here in brown or red is just the semiconductor, and these brighter lines here are metal, and in here are the 2 points where basically by applying voltages to these gates you can capture single electrons ultimately. Right, and so the other system is are defects in things like diamond, which also have very coherent spins. If you look where the industry puts their money on, it's mostly on solid-state qubits. Google is investing very heavily into superconducting qubits. Intel has an investment into spin qubits, and I think Microsoft is doing something in between. They're investing in semiconductor, superconductor heterostructures that are going to host, hopefully, these topological qubits. So I'm gonna focus entirely on these spin qubits. Okay, so here's another summary of spin qubits. So okay, I already said that typically we're thinking of spin 1/2 particles, electrons, sometimes atomic nuclei. This is the qubit. Basically, the qubit states can be depicted as points on the surface of a unit sphere, where the north pole is the spin up or zero state, the south pole is the spin down or one state, and all the points in between depict the superpositions of these two states. So basically, superposition of this state with this state can be written as, okay, I mean, maybe I can write it on the board. So any state of a single qubit, and you've probably seen this before, you can write. So I can use basically some parameterization. Maybe I should. So basically I have two complex amplitudes for arbitrary quantum superpositions. I can choose this one to be real because the global phase doesn't matter. And then basically this angle theta, this controls how much zero content my state has and how much one content. And this phi here controls the phase between the two. And these two angles these are basically spherical coordinates on the surface of this sphere. So theta is basically the latitude here, so it tells you how far down you are. So the equator here would be theta equals pi, I think, right? And then phi is the angle around here. So with these two parameters, you can parameterize all pure states of a single qubit. You've probably seen this before, but in case you haven't, this is very useful. This is what we call the Bloch sphere. For optics, people call it the Poincare sphere. It's basically the same thing. Okay, so these are the states of a single qubit. Of course, it gets more complicated if you have more than one qubit. Then you can have superpositions of products of these zeros and ones. Okay, so one realization is electron spins in quantum dots. And I think what's really an advantage is that these systems can have long coherence, and they're magnetic objects, they're spins, they don't have an intrinsic electric dipole, so in principle they're robust against charge or electric noise. Of course, sometimes when you want to control the spins with electric fields, you're going to give up some of this in order to be able to control the qubit more efficiently. Okay, so here I've tried to summarize more or less the state of the art. Maybe this is not totally up to date. So that people can now fabricate strings of quantum dots. Here's one example with 5 quantum dots. People I think in Jason Petta's group, they have this a device with 6, or they make even more, and they can fill these quantum dots simultaneously with single electrons. So this is basically the first step, but it's not, of course, it's not all you have to do. You have to control every spin then individually. So basically what people can do nowadays is they can have 2 spins, they can make single qubit gates on either of the spins, and they can make 2 qubit gates on the pair of spins. Scaling up of these things is in progress, but I think it's to be seen how far this will go. Okay, so this was basically the introduction of the introduction, and now I'd like to go more deeply into some more detail, how we model this theoretically, and also some issues, already discussed some issues that have been encountered when trying to implement these spin qubits. So going back to my sketch here, I want to know a bit more precisely what actually has to be done. So maybe I should make this sketch a bit more precise. From a physics point of view, what's happening is actually that my quantum box is, because it's some quantum mechanical system, it's going to be governed by the evolution given by the Schrödinger equation, or basically there will be some Hamiltonian that describes this quantum system, and the evolution of an input state will basically be given by this unitary, which is generated by this Hamiltonian, right? So what I have to do is I have to somehow write my classical input state into some input quantum state, and then feed this into the quantum computer. The quantum computer will carry out this time evolution. There will be a final state, and then I will do some quantum measurement, which will give me again a classical answer. So that's kind of the standard model. And so here's a bit more, a more precise description of what this amounts to. So in principle, I have my qubits here. So now I depict all of them with this Bloch sphere representation. Initially, what I want to do is I want to prepare all of them in some initial state, let's say all of them in 0. You see all these spins point up now, they're all 0. And then I have to carry out this big unitary. I mean, maybe these are not only 3 qubits, but maybe many qubits. So this is going to be a huge unitary matrix, if you want. And then in the end, I want to measure the qubits, maybe some qubits or all qubits individually. So basically, one by one, I can measure these qubits. And this picture is a bit deceptive because usually, if I have, usually this will not be a product state. So this state will not be able, we will not be able to factorize this state into the state of one qubit, the next qubit, and so on, because they can be entangled, right? So this, maybe I cannot really draw these arrows. But of course, I can arrange the algorithm such that this is a product state. And what I've already described before is that this unitary can be split up into smaller pieces, basically single qubit gates. And single qubit gates are nothing but rotations from the group SU2. And you can, this algorithm could consist of many such gates. And then there are gates that act on 2 qubits. And for instance, this controlled NOT gate, which I will explain in a moment. And then in principle, there could also be gates that act on more qubits, right? And the question is, do we really need this? Of course, this is probably harder to do than single qubit gates and 2 qubit gates. And there's a very nice result from 1995 that if you have single qubit gates and only one 2 qubit gate, namely the controlled NOT gate, then this is universal for quantum computing. This means that any unitary that you give me, I can split up into a series of only controlled NOT and single qubit gates. And so that's very important because it tells us that what we need to do is only one 2 qubit gate and not every 2 qubit gate and no 3 qubit gates and so on. This is not the only possibility, but it's one possibility, and it's very encouraging, of course, that this is possible. Okay, what is the controlled NOT gate? You may have seen it already in the course of these lectures. I can define it on a basis. So the basis here means that I input here a product state where this state is either 0 or 1, and this state is also 0 or 1. In the context of the CNOT gate, this upper qubit is called control bit, and the lower one is called target qubit. And what it does on these basis states is basically flips the target qubit if the control bit is 1. So if the control bit is 0, nothing happens, the same output state. If the control bit is 1, then the output bit, the target bit will be flipped. So that's why it's called a controlled NOT. It's essentially a NOT operation, logical NOT operation on the second qubit, controlled by the control qubit. So far, this is only a classical operation, but of course, you can now, but the idea is that this is linearly extended as a linear operation, and then it means you can also input, for instance, superpositions as a control bit, and then you get a superposition of what you would get with a 0 here, so this is 0, 0, or with a 1 here, which is 1, 1. And so this is already an entangled state, and you see now you cannot write this as the product of 2 qubit states. So I cannot write there are no states phi and chi for which I can write this as a product. This is called entanglement, and it's an important ingredient in quantum computation. It's equivalent. Yeah, you could define it. Basically, you get this other controlled NOT, where the role of the control is inverted by just adding a NOT gate here and a NOT gate here. And it's also universal, of course, which you can see by just putting NOT gates here. Right? And there are other universal 2-qubit gates, which are really not equivalent to CNOT. Okay, other questions? All right, so the model I'm using for spin qubits is essentially, motivated or, basically driven by this picture of a chain of quantum dots that's defined in a semiconductor heterostructure, where you have a series of quantum dots with one electron in every dot. I'm writing here a Hamiltonian that has exchange coupling, so this is nearest neighbor coupling between the spins, and this is generated by virtual hopping of the electrons. So it's just an isotropic exchange coupling, and basically I want to control the magnitude of the exchange coupling by changing the voltage on this intermediate split gate. So this is one way how this can be done. And then basically the idea is that this will lead to 2-qubit gates between the 2 qubits. Let's say if I switch this exchange coupling on between spin 1 and spin 2, then I will be able to use this to construct a CNOT gate between these two. Actually, what will directly be generated is a so-called square root of swap gate, which is also universal for quantum computing, and this has been demonstrated already more than 10 years ago by Jason Pedder and collaborators. And the other thing I need is, of course, 1-qubit gates, and for this, in principle, what I need is local fields. So I need to rotate a spin, so I could do this with magnetic resonance or by applying a pulse of a magnetic field. That's why this field has to be time dependent, and it's local. And the electron spin resonance version of this has also been implemented at TU Delft by Frank Koppens and others. And so this is basically realizing a single qubit gate. And together, I mean, these were two different experiments, but if you manage to combine these two features, in principle, you can do universal quantum computing with such an array. So this is my model.
What is the form of J of T?
Okay. So here, I've put here the Zeeman energy, and I made the magnetic field time dependent. So that's one way how you could control single spin rotations. Another way would be if, let's say, I mean, this is something hard. It's hard to change the magnetic field here, but not here. And so then another idea is that you would change the G factor. So the Landé G factor, in principle, in such a semiconductor heterostructure, can be manipulated electrically. Let's say if you have a kind of 2 layers of 2 different materials with different effective G factors, where the electron has different G factors, and you can push the electron with a top gate from a top layer into the bottom layer. So you could control this G factor electrically. So that's another idea how, in principle, this could be done.
And also, what about J?
Oh, J.
J, yeah.
So, what was the question? Okay, I'll get to this. This is the next step. So, okay. How do I get? I mean, what is the exchange coupling? How is it determined by microscopic parameters? Yes, that's the next slide. Yes. So how can I see now that these are robust against charge noise? I mean, that's a very good question, because basically they are robust when this is 0. So basically the idea here is that whenever you're not doing any operations, you would switch these off, and the spins would just be sitting in their quantum dots, and basically, okay, in the absence of spin-orbit coupling, which I have omitted here, the spin is completely decoupled from the orbital motion. And in that case, any electric fluctuation would not affect the spin. But actually, it's a good point that while this is on, there is charge. The electric field will actually have an influence on this. And so when this is on, then charge fluctuations can matter. And there are other effects. So this is only, I think it's only an approximative statement. But I would say the other extreme would be if you make, instead of a spin qubit, you would make a charge qubit. I could also say, well, looking at these 2 quantum dots, let's just take 1 electron, and my qubit would be the 0 state is if the electron is here, and the 1 state is if the electron is here. That we would call charge qubit. And that would be directly strongly affected by electric noise. And so that's basically the contrast that I'm trying to make. So this you can actually do with this charge qubit, but the coherence times will be much shorter, typically. Okay, so in the next step, I'd like to give you more information about this exchange coupling. How does it work? It's based on the exclusion principle. So essentially, you can have, if you only look at one orbital in this quantum dot, the only degrees of freedom you have are the spins, and you have two spins 1/2. Each of them have 2 positions. So in total, you have 4 different states: up, 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 down, down, up, down, down, right? And you can organize them in a slightly different way in terms of their total spin. So if you have 2 angular momenta, you can add them. If you add 2 spins 1/2, you get either spin 0, spin singlet, or you get spin 1, spin triplet. And so there are 3 spin triplet states and 1 spin singlet state. And in the spin singlet state, this is a state that can also exist in one dot, in one orbital. So now, actually, this is now where the exclusion principle enters. So I have now now I'm drawing energy or potential versus position. And so these are my 2 quantum dots. And I'm looking at only one orbital level. And I can put 1 electron. And here I can put 1 electron. I can put a second electron if it has the opposite spin, right? So in this case, this electron can hop onto the other side if the 2 dots are close enough and there's tunnel coupling. So this is possible for spin singlet, but not for spin triplet. So any of the 3 spin triplets are blocked by the Pauli exclusion principle, because it would mean that you put 2 spins with a symmetric spin wave function into the same orbital wave state, and that's not possible. So what's the dynamical meaning of this? Basically, it means that the triplet has just some energy given by these localized orbitals, while the singlet is corrected by this hopping. So there's this virtual hopping. You can do second-order perturbation theory, or there are different methods that you can use. And basically what you get is that the energy of the singlet is lowered by an amount that's given by this tunneling matrix element squared divided by the energy cost of putting 2 electrons on the same dot. So basically this U here, this is a Hubbard U, for those of you who know the Hubbard model. So this is just the energy cost of putting, Pauli principle allows you to put 2 electrons on the same dot, but there will be Coulomb interaction, and this will increase the energy of this state versus this state. And this energy difference is called U. Okay, and so basically the singlet, and you see if this U is too large, if this U goes to infinity, then basically the effect goes away. Because again, the Coulomb interaction would prevent this. But because this interaction is finite and this hopping is finite, you get a slightly lower energy for the singlet. And the exchange coupling is simply the energy difference between singlet and triplet. Right? So now I have an energy difference which only depends on the spin state. And this is the exchange coupling. So this energy is just given by, in this case, by 4t squared over u. And so what is the spin Hamiltonian? So if my electrons are sitting each in one dot, and one of them can just virtually go over and back, but basically I'm now projecting everything into the sector where I have 1 electron per dot, I will get a spin Hamiltonian. I can describe the state purely by its spin. And this I can simply write as the exchange energy times the projection operator on the singlet plus some constant. Right? So basically this Hamiltonian only encodes this information that the singlet has a lower energy than the triplet. That's all. It's just the projection operator on the singlet state. Okay? And now you can also write this projection operator in terms of spin operators. So this is the projection operator on the singlet. So it depends on total spin, right? So I can write it in this way. You can guess this formula if you want. So basically if S is 0, this is 1. And if S is 1, this is okay, this is the operator S square, and the operator S square has its eigenvalue S times S plus 1, right? And so if S, small s here is 1, then this S square is 2, and this is 0. So this is just an expression of the projection operator in terms of the total spin operator, S squared. And now the total spin is given as S1 plus S2. So I just have to write out the square of S1 plus S2. I can just write out the square. And then this S1 square and S2 square, these are constants because these are spins 1/2. So this, I can use this formula again. These are just 3/4. And then what I'm left with is up to a constant is this S1 dot S2. So basically this up to a constant, this singlet projection operator is given by S1 dot S2. And so this is in some sense a simple derivation of the Heisenberg spin model, which is generated by this virtual hopping between dots. Okay, so this is the projection operator on the singlet, or if you wish, on the antisymmetric spin states. So these are the spin states that are antisymmetric, or they change their sign under exchange of the two electrons. All right, so that's basically how this exchange coupling comes about, and it really is based on the exclusion principle, and it's really based on the fact that there's only one orbital here. Right, so only if this is a single orbital, this will work. Yeah, so basically, so imagine, so there's a wave function. So now it is, there's an orbital, yeah, exactly. So there's an orbital wave function here, and the singlet can extend its wave function a little bit, right? It hybridizes a little bit with this state, so its wave function is going to have a longer tail, and that actually reduces the kinetic energy. That kinetic energy is gradient of the wave function squared. That's the reason. Okay, any other questions? So this is the basis. Okay, this constant you can drop. Okay, so how can we use this now to make quantum gates? I claimed that you can use this to make controlled NOT, and maybe I should really tell you how this works. So now we know the Hamiltonian. It's the Heisenberg exchange Hamiltonian, and we know it's a projection operator. That's quite handy. I write it here as the projection on the anti-symmetric spin states, and now I can exponentiate it. So if I want to know the quantum time evolution when I switch on the exchange coupling here, I can exponentiate this Hamiltonian. And okay, all right, so this, what I will do is make this J here time dependent, but J is a number, and so it means that this Hamiltonian will still commute with itself at different times. This is useful because I don't have to put time ordering here. So I can just integrate this. What I will get is e to the I phi, and phi is simply the integral over J. Here I have assumed that this J is constant. So I switch it on abruptly and switch it off abruptly. I could also write here integral over J times this projection operator. And what's nice about this is that it's very easy to exponentiate projection operators, because when you square a projection operator, you get back the same projection operator. And so you can write this as an exponential series, and basically all the so you get 1, and then all the higher terms, I mean, there are powers of this operator, but all powers are just the operator itself. It's very useful. And the prefactor is just the entire exponential sum without the first term, right? And so I can just write e to the I phi minus 1. So if you don't believe it, you should try it yourself. So it's very easy to exponentiate this. So what I'm doing here is, what I imagine is that I have this, when I have a pulse of this exchange coupling is usually turned off, and I switch it on at some time t equals 0, and I leave it on for some time. And so this phi angle here is basically given by the area under the pulse. I could also use a soft pulse, it doesn't matter. And let's say, if I can try what happens now if, by feeding in some state, let's say up, down, and see, asking myself what comes out. So I can, for instance, choose this area here such that I get exactly pi, pi pulse exchange. And if I do that, so then this phi is pi and e to the I pi is -1. So I get here 1 minus 2 PAS, and this is a swap. So, okay, now you have to think so. But what this does is, if I act, so this is the projection, this is also the projection operator on the singlet. So basically, what this says is, if I'm in the triplet, then this is 0, nothing happens. If I'm in the singlet, then this is 1, and I get a -1. So in the singlet, which is anti-symmetric, I get a minus sign, and in a triplet, which is symmetric, I get a plus sign. And in the end, so this I can write as a linear combination of singlet and triplet. And, okay, you can do the math. I mean, what comes out is that this exactly swaps the two states. And in some sense, that's the reason why this is called exchange, right? This exchanges the spins. But actually, this is not a very useful gate for quantum computing. I mean, maybe it's good for routing qubits, if you want to change the position of 2 qubits, but it's not a universal gate for quantum computing. But now we can do something else. We can use only half the area, and so swap is something you can also do classically, right? You can swap classical bits. But this is a continuous operation. You can stop at any time before you have completed the swap, and that's something you cannot do classically, right? You cannot swap 2 classical bits halfway. You either swap them or not. And so here, you can stop in the middle of the swap operation. So you choose phi equals pi halves, and the question is then what comes out. And if you do the math, what comes out is a linear quantum superposition of the input state and the swapped state. And this is again an example of an entangled state. So this is an entangling gate, and you can also show that this is universal. So this is square root of swap, and actually it's easy to, you can plug in here pi over 2, and you will find that this is a linear combination of the unit operation and the swap operation, and this gives you this state. So this is an entangled state, or EPR pair. So that's the first indication that this gate is doing something really quantum. And actually it's sufficient to do anything quantum mechanically. So basically one way of showing this is that you can make a sequence where, this gate here, this is now called U of t. This is combined, so maybe I can show you this circuit. This is this square root of swap, and you combine it with some single qubit operations, and what comes out is control NOT. So once you have shown this, is of course, you know that this gate is also universal for quantum computing, because you can use it together with single qubit operations to make CNOT. All right. So this is how it's working in principle. There are actually also other ways. So what I've shown you now is a model where you switch on one interaction, then you switch it off again, and then you switch on another interaction. Okay, so how do you switch on? So what you need to do here is you need to switch on this J. So there's more than one possibility. One that I've alluded to before is basically you change this. So basically this tunneling here depends on the barrier height between the two quantum dots, and this you can control with these electrostatic gates. That's one way. Another way is to detune the energies of the two. While it's on, of course, this J may fluctuate because the gate voltage will fluctuate, and then this will give you some error. That's only while you're making the gate. Okay. So this alternative method would be that actually you can switch on different interactions at the same time, right? So what you can do, for instance, you can switch on this exchange coupling and then a magnetic field gradient at the same time. So it's magnetic field and the gradient. And if you do this, you can actually make CNOT in one step. You don't have to make such a long sequence. This is also possible. And actually this is interesting because people are now designing magnetic field gradients using micromagnets that lie on the top of these structures. Okay, let me summarize some experimental. So this was a lot of theory, and I'd like to summarize somehow some experimental, basically achievements that have been done in a semiconductor material which was very instrumental, namely gallium arsenide. Yeah. Okay, you may want to detect the entangled state, or you may want to keep on computing, right? So usually, I would say that the goal of most of these standard quantum algorithms is not to make an entangled state, but to somehow create an output which you can read classically. But you could also do, of course, you could try to detect this entangled state. Then you would do something like quantum tomography. But okay, I was just showing how to make the gate here. Okay, so what has been achieved? So one is, of course, one of the first steps was to really put one single electron into a quantum dot. And this was not so easy, but it took a while to do this. And I think these experiments were the first ones where people really put single electrons in these semiconductor quantum dots around 15 years ago. And then so these are gallium arsenide heterostructures with metallic gates on top. And basically, what happens is that when you put fewer and fewer electrons, you make these gates here more and more negative. And then basically these contacts here pinch off. So basically you close the system to the, towards these reservoirs, electron reservoirs. So you cannot measure the typical way to measure occupancy here is by running a current through the quantum dot. So this is called Coulomb blockade. You see a peak whenever there's another electron added to the, or removed from the quantum dot, and you can sort of see how you remove electrons one by one. But the problem is, as you empty this dot, these contacts will not be conductive anymore. And one of the tricks was to use here a conducting channel that's nearby, and that's only capacitively coupled. So this is a so-called quantum point contact or charge detector. And this can be then used, the conductance of this is still finite while you're here pinching off this, or emptying this quantum dot. So what also was done then sort of almost at the same time with this is to, once you had a single electron, apply a magnetic field and measure the spin lifetime, T1. So it means you prepare the system in the higher lying, energetically higher lying spin state, and you wait for some time, and then you see if it's still up there or if it has decayed. And this T1 time has been measured for the first time in these experiments. And later, this T1 time has been measured as a function of the external magnetic field. And what was found is that as you decrease the magnetic field, the T1 lifetime goes up. So this is wrong. This should be 1 over T1. But this is the decay rate. So this becomes smaller and smaller. And so here, at the lowest magnetic fields, the spin lifetime exceeds 1 second. So already quite early on, we could see that the spin lifetimes in these gallium arsenide quantum dots can be very long. So this was very promising. I already mentioned that single spin ESR was done using charge detection. So this cannot be magnetically detected, but by charge. And this uses essentially the Pauli principle. So you prepare here 2 spins up, which are blocked from tunneling, and then you use electron spin resonance to rotate one of the spins, and once it's rotated by 180 degrees, you have down up, and then this electron can move, and you can measure it with a charge detector. That was done at TU Delft. Then I've already mentioned this experiment, landmark experiment at Harvard by Jason Petta and others, where they implemented the square root of swap, and this actually was very fast. This exchange coupling is a very strong interaction, and it allows for square root of swap in a time below 1 nanosecond. They have measured T2, this is the spin coherence time. I'll say later more about this. This was found to be much shorter. So T2 star, if you average over many runs of the experiments, this turned out to be fairly short, only around 10 nanoseconds. And this already pointed to the problems that we have found in this material. You can extend this T2 time by using spin echo and generalizations of spin echo, where you use many pi pulses. And so you can, okay, I think this exceeds here, this T2 time exceeds 200 microseconds. This was still in gallium arsenide. But actually, so there are problems, and I'd like to use this point now to highlight some of the challenges that one was facing at this point. So again, yeah, I have these two interactions that I would like to use for quantum computing. One problem is that making these local magnetic fields is very hard. I mean, this was achieved for a single spin, but it's clear that this is very hard to make, to rotate only one spin. You need to somehow be resonant with only one spin. And so you need magnetic field gradients or whatnot. So this is definitely a hard thing, and it would be much easier, or in some sense much better, to use electric fields. And so one way this could be done is use multi-spin qubits. And I will come back to this a bit later. Yeah. So these experiments are typically at low temperature, so below 1 Kelvin. I mean, this is basically one thing is that you have here higher states in your quantum dot. There may be this energy splitting is maybe on the order of milli-electron volt, or 1 milli-electron volt is about 10 Kelvin. So you don't want to thermally excite this. You don't want to thermally. Okay, the temperature is often higher than the Zeeman splitting. So this is a dynamical open system. So although the equilibrium temperature may be higher than of the environment, may be higher than your qubit splitting, of course it depends on this T1 time, how long it takes to relax to the equilibrium. Since this is very long, you don't care. Yes. No, I will come back to T1. So the question is whether this explains whether T1 is long at low magnetic fields. This has a different, so this T1 was already in the low temperature limit. T1 will be suppressed if you increase temperature. I will come back to that at some point later in the lecture. Okay. So this is one problem I'd like to come back to later. And then the other problem is basically this short dephasing time that was found in the 2005 PETA experiment, and it was found that this is due to nuclear spins. And actually, so this is an important observation, that in these systems, these 3-5 semiconductors, even if you manage to put only a single electron into your quantum dot, you're still dealing with a lot of spins, because there are a lot of other spins around, and these are the spins of the atomic nuclei. And so this is basically because in these materials, every atom has a nuclear spin, and they all interact with the hyperfine interaction here with your electron spin. And so ultimately, this is a materials problem, or this one, it could be a materials problem, and this is something I'd like to show you now. But maybe before, I should also say a few words about what this spin relaxation and decoherence actually means. So this is a terminology that I've already used, and probably others have been using, and maybe it was introduced. So, but just to be sure, I'd like to reiterate here. So one important timescale of a qubit is a spin relaxation time, or qubit relaxation time, and basically it describes the following phenomenon. If you prepare the system into the excited or a higher energy qubit state, let's say 0 spin up here, then basically by interacting with its environment, this system can shed its Zeeman energy, its qubit splitting energy into the environment by flipping to the spin down at some point. And basically this is often an exponential decay. So if you look at the Z component of the spin as a function of time here, you get an exponential decay, and the time scale is what we call T1. So this is spin relaxation. And the other time scale is spin decoherence, and this describes a situation where you prepare a transverse state, so a coherent superposition of 0 and 1. So in this Bloch sphere representation, this would be a point which is on the equator, of the Bloch sphere, and if there's an externally applied magnetic field, so the qubit energy levels are split, and this state will be non-stationary, will actually precess around the external field. And so when you measure, let's say, one of the transverse spin components as a function of time, you will see a cosine oscillation, and this is a hallmark signature of spin coherence. Now, if this system interacts with the environment, without even exchanging energy with the environment, it can lose its phase coherence. So basically, imagine that this magnetic field, which splits the two levels, is slightly fluctuating. So it means that the speed of this precession is not exactly constant, but it's fluctuating in time. And so it means you lose track of this phase after a while. So basically, you still know that the spin is in the plane, but you don't know in which direction it's pointing. So we have lost phase coherence, and this we describe by a density matrix, which is an incoherent mixture of spin up and spin down. And if you measure, let's say, the x component of the spin in this state, you get 0, because it's just averaged, it's an average of all possible directions. So that's here in the infinite time limit. And very often, this is also an exponential decay, not always, but very often, this is an exponential decay. And in this case, we call this the T1, the characteristic time scale, the T1 time, T2 time. And obviously, for qubits, what you would like to have is that the time scale on which you can make quantum gates, that I call tau up here, should be much shorter than the time scale over which this qubit degrades either by relaxation or decoherence. Okay, so maybe one more connection to the theory of open systems. So basically what I'm using here is actually a description in the Markovian limit. So if you do general system bath theory with a single spin, you can describe your spin by a density matrix, a 2x2 density matrix. And actually an equivalent description is the Bloch vector. So it's just a trace of the vector of Pauli matrices multiplied into the density matrix. So this vector is just a 3-vector where these are the 3 Pauli matrices. And these are then the components of the Bloch vector. And these are exactly the point, these exactly describe, if this is a pure state, these describe points on the surface of the Bloch sphere. And if these are mixed states, they describe points in the interior of the Bloch sphere. So basically now we have an extended interpretation of the Bloch sphere. It's just the surface of a ball which contains all the mixed states of the qubit. And at the center of this ball here is the unit matrix, which has where you don't have any polarization left. Okay, and then the dynamics of this Bloch vector can be described with the following equation, the Bloch equation. P dot, so this you can plug this in here, and then you have rho s dot, and here you could put the Lindblad equation, and you can derive this Bloch equation, and if you're interested, you can look it up somewhere, and if you don't find it, then you can look up a review article. So basically, it's a rotation about the external field. So this omega here is the rotation axis, and that's just a coherent rotation about the externally applied field, or a rotation axis omega. And then there's a relaxation matrix R which describes decays that I think were shown. This was shown very nicely, very graphically yesterday in Michel Deveray's talk. This is basically equivalent to this octagon which shrinks. So there are 2 ways this can shrink. T1 describes this uniform shrinkage, and T1 this shrinkage towards the z-axis. And this is described exactly by this equation. And P0 is simply the equilibrium state. This depends on the temperature. This could be the ground state if at 0 temperature or some other state. Okay, so that's basically the description. And this equation, if you solve this, this will always give you exponential decays. And this, in some sense, you have put in by making the Markov approximation. So this is for the experts on open systems. These exponential decays, these have to do with this, the way you describe here the dynamics in the Markov limit. The noise, that's all contained here in the relaxation matrix. So this is a, maybe you're thinking in terms of a classical Langevin equation where you have a fluctuation term. Here you don't need this because you have, I mean, this is all contained here. All right, now let me show you an example where actually we have an example of non-Markovian decay, so where the decays are not exponential. And this is this nuclear spin-induced dephasing. So I said this is one of the problems when you work with gallium arsenide, that you have all these nuclear spins sitting around and interacting, each of them interacting weakly with your electron spin, but the number of nuclear spins is typically 1 million or 100,000 or something, and this is, in total, this gives a noticeable, very strong effect. So the way you can describe this, in a most simple way you can describe this, I think, is to look at the Hamiltonian or the dynamics of the spin here, of the electron spin, described by the SZ component, in an external field which points in Z direction. So this B is just G mu Bohr BZ. And then there's a nuclear field. So I can describe the hyperfine interaction here by this quantum operator. This is just another way to write the hyperfine interaction as an effective nuclear field. I think we also have heard this. This is the Overhauser field. The point is that this Overhauser field originates from the nuclear spins, and the nuclear spins are quantum objects, and so this is a quantum operator. Okay, so basically the electron spin sees the combination of the externally applied constant field B and the nuclear field Bn. And here I've already neglected all the components of Bn that point in the plane because they will be suppressed by this B here. So what happens now if you start with a nice pure state, which you prepare here in the equator of the Bloch sphere? You know, in the coherent case, let's say, okay, time evolution you can describe now with this Hamiltonian. And I start with this electron spin state and the some nuclear spin state. Okay, and now I want to look at what happens to the state. And let me first look at the case without nuclear spins. Without nuclear spins, I simply have a precession about the external field. And if I measure, for instance, Sx, I will see a nice cosine. Okay. Now, the next case is, and okay, this cosine, I should say that the period of this cosine is given by 1 over the external field. Now, if I switch on the nuclear spins, in general, this will be very complicated, but I can look at one sort of unrealistic special case where the nuclear spins would be prepared in an eigenstate of this operator. If that were the case, then I can replace this operator by its eigenvalue, and essentially this just adds to the external field, and essentially then there's still a cosine, but the period is given by 1 over B total. This is simply the sum of the externally applied field and this nuclear field. So in this case, the nuclear field is sharp. It's like a classical field. But that's not very realistic. Usually the nuclear spins are not going to be prepared like this. All the nuclear spins will be random. And so much more realistic is that I have a totally unpolarized nuclear state. If typically the temperature is much larger than the nuclear Zeeman splitting. Nuclear spins have a much smaller magnetic moment than electron spins, and so even at low temperatures, typically the temperature is much larger than the nuclear energy splitting. So to good approximation, I can assume that the nuclear spins are totally unpolarized and their density matrix is just proportional to the unit matrix. So then I can write a probability distribution for this nuclear field. So basically for this operator, I cannot substitute one eigenvalue. I can substitute some eigenvalue, and then I have to sum up or average over all these eigenvalues with a certain probability distribution. And this probability distribution I can derive from this unit matrix here, the delta function. And basically, maybe the easier way to think about it is assume the nuclear spins are spin 1/2, and they can be randomly up or down. So you have basically n, big N, so if you have big N nuclear spins, each of them is either up or down, then what distribution are you getting? Do you know what distribution you're getting? Sorry? Yeah, each nuclear spin is randomly up or down with 50% probability. Sorry? Yeah, Poisson is correct. I think for small n you would get a binomial distribution, but then of course n is large and you get the Poisson distribution. And actually if n is large and the average is, so basically in the end, in a large n limit, you can approximate the Poisson distribution by a Gaussian distribution. But it's absolutely right. You get a Poisson distribution, and we approximate it by Gaussian. So essentially, the nuclear field is random, and it has a probability distribution like this. Its average is 0, and it has a certain width sigma, which is given by the hyperfine coupling divided by square root of n. Big N being the number of nuclear spins. Yeah, the nuclear spins, that's a good point. For the time being, the nuclear spins, because they have this small magnetic moment, at the time scale where the electron does its dynamics, the nuclear spins are basically fixed. Okay, but they're random. So when I repeat the experiment, they will be different. You will sample a different nuclear field from this distribution here. Okay, so now you can basically, again, look at the time evolution of our initial state here in every nuclear field, and then average, and what you get here is some Gaussian decay of the coherence. So this is the density matrix of the electron spin. So initially it's here 1/2 times 1, 1, 1, 1. And without the nuclear spins, you would just get this rotation of the phase here. With the nuclear spins, you get this exponential decay, this Gaussian decay. So what we get here is, if you then use this density matrix to calculate, let's say, the x component of the spin, you get a cosine which is suppressed by a Gaussian. And the time scale of this, I call tau here, is given by basically 1 over the hyperfine coupling. And so this is, strictly speaking, not a T2 time because it's not Markovian. So this is not a exponential decay, but a Gaussian decay, which first goes very slow and then becomes faster. Okay, so you can put in numbers for gallium arsenide. We know we have some estimate for the hyperfine coupling. Typically, in we know how large these quantum dots are typically are. Order of magnitude is 100 nanometers. We can estimate how many nuclear spins the electron wave function overlaps with. It's about 1 million. And if you plug in these numbers, you get a coherence time of about 10 nanoseconds. That's about what was measured. Okay, so summarizing, we know that nuclear spins are unavoidable in gallium arsenide. I'll make a point about this in a minute. And we have known before that for mobile electrons in gallium arsenide, the coherence time is limited to maybe 100 nanoseconds, and we also speculated that this was going to affect the spin coherence in a quantum dot for localized electrons, and this was confirmed. And I think we understand more or less why this happens. So then the question is, how do we go forward? These nuclear spins are there. So what we can try is to either control the nuclear spins to make their state something else than this random superposition. That's very hard, but you can try. Or you can try to get rid of the nuclear spins. So this would be the more radical solution, and this would automatically lead to new materials. So let me say one thing about preparing the nuclear spins. This actually has been done by the group of Amir Yacobi at Harvard. This is actually quite interesting. So in some sense, you could say this is a path engineering in an open system, right? So the nuclear spins are our quantum environment, and we're trying to engineer it in such a way as to give a better electron spin coherence. What you can do, so if you can use this effect of spin blockade. Again, this is this Pauli exclusion principle. If you have two quantum dots, you fill them with one electron in each dot in a spin singlet state. You can move one of the electrons to the other side. This is allowed. But if you're in the spin triplet state, this is blocked. However, if you also have nuclear spins, let's say if there's a nuclear spin sitting here with its spin down, then what you could do is you could first flip-flop electron nuclear spin with hyperfine, and then you could move. Right? So then you can unlock this Pauli blocking. And so if you drive a current, which is every now and then is blocked in this spin triplet state, then basically while you're doing this, you're constantly flipping nuclear spins, and you're only flipping them in one direction. So this is one way of preparing the nuclear spins. You can reach nuclear spin polarizations of maybe a few % with this, but not, I mean, this is very far from completely polarizing the nuclear spin environment. But you can reach basically situations where you can see the Oberhauser field and you can even use it to do spin manipulations. Yeah, this is one way of dynamical nuclear spin polarization. There are others. Okay, so okay, so actually, why are there always nuclear spins in gallium arsenide? So I have a slide called Nuclear Spins in 2 minutes, and I always hope that there are no nuclear physicists in the audience. So this is my very basic understanding of why gallium arsenide has nuclear spins, and there's no way around it. So basically, if you look at some atom, let's say here's helium-4, consists of the atomic number Z, here it's 2, it determines the number of protons and also the number of electrons to make the atom neutral. And then you have some number of neutrons, in this case it's also 2, and the atomic mass is the sum of the number of neutrons and protons. All of these subatomic particles have spin 1/2, and the total spin will be some sum of all these. Okay, so then some facts that I'm not going to prove, so I don't know enough nuclear physics to know it, but it turns out that even proton numbers are more stable than odd numbers, but the proton number in some sense we fix by choosing an element, right? But the same is true for neutron numbers, so even neutron numbers are more stable than odd neutron numbers. So that's why I think one reason why, you know, most of the helium you have, if there's any helium left, I don't know, on Earth, is helium-4 and not helium-3. So it means if atomic number is odd, then if you also put an odd number of neutrons, that's very unstable because it's odd-odd. Much more stable is odd-even. So for instance, one example is lithium, Z equals 3 and N equals 4. Sorry, N equals 4, yes. That's most of the lithium is in this form. So it means the upshot is that even atomic number usually implies even atomic mass for the most abundant isotopes, and odd atomic number mostly implies odd mass for most abundant stable isotopes. And then also another ingredient you need is that the lower spin nuclei are typically more stable. So if you put these things together, it means that if you have an even atomic number, then usually the zero nuclear spin is most likely. One example is carbon. Right? Carbon has Z equals 6, and 99% of carbon is Z12, has zero spin. And if you have an odd atomic number, and this is the case of gallium and arsenic, then usually then you have an odd number of nucleons, because then you combine it with an even number of neutrons, you have an odd number of nucleons, and the total number of nucleons is odd. Odd number of spin 1/2s can never have a spin 0, so it will have a finite nuclear spin. And if you look at the periodic table, this is more or less what you see. So here's gallium, here's arsenic, and so this red number here is the fraction of naturally occurring nuclear spin-free isotopes. So the fraction of nuclear spin 0 atoms that occur naturally. And all these column 3 and 5, there are no stable isotopes with 0 nuclear spin. So basically, there's no way out here. You cannot get rid of the nuclear spins for gallium and arsenic, whereas in column 4, you have mostly spin 0 nuclei. So carbon has 99%. Silicon consists mostly of silicon-28, which has 0 spin. Same for germanium. So these would be good candidates now for spin qubit materials. So I'll talk a bit about carbon this afternoon. So carbon comes in many forms, as you know, and one form that would be sort of similar to these 2D heterostructures would be graphene, which also it's a 2D semiconductor. The only problem is that it doesn't have a band gap, so it will be hard to localize electrons, so you have to engineer a band gap. Then there's diamond, and I've already said that defects in diamond are very coherent, have very long spin coherence times, and this is partially due to the fact that carbon comes mostly as a nuclear spin-free isotope. Then there's silicon, which is of course the workhorse of conventional electronics, but for quantum For quantum applications, this is fairly new, and about 5 years ago, people started to switch from gallium arsenide to silicon, and now I think most people who work on spin qubits in semiconductor quantum dots use silicon in one form or another. And I should also point out that one advantage of these materials is that although not all naturally occurring isotopes are nuclear spin-free, of course, since there is a nuclear spin-free isotope, you can in principle isotopically purify them and then even improve on this. There's also silicon carbide, which is similar to diamond, which is promising. And then there are these other 2D materials that consist of transition metal dichalcogenides, and all of these have relatively low concentration of nuclear spins. So these are all interesting materials for spin qubits in principle. And maybe I'll talk a little bit about these, because these are real semiconductors with a band gap. So I'll talk about these tomorrow, I suppose. Okay, so let me just highlight here. So this is a slide that I stole from Lieven van der Sijpen. So maybe just to show you what happened in the last 5 years when people switched from gallium arsenide to silicon. So gallium arsenide, you have your electron spin surrounded by 1 million nuclear spins, T2 star. This is the coherence time, the decay time of this, the envelope of this cosine oscillations. If you average over many shots, it's only 10 nanoseconds. And the spin echo takes you up to maybe 200 microseconds. If you use natural silicon, this is what people have been doing or still are doing, you can immediately get T2 stars on the order of a microsecond. And some people are even using isotopically purified silicon, and then they gain another 2 orders of magnitude. These coherence times are now really long. This is without even doing spin echo. And then there's some other development where people are putting back some spin into silicon by putting donors inside. And these donors can also, both the electron spin and the nuclear spin can have very long spin coherence times. Okay, this is something, let me just mention it and I will come back to it this afternoon. Actually, these group 4 elements are interesting in terms of nuclear spin induced dephasing, but by switching from gallium arsenide to silicon, you do change a few things, and the material is really not exactly the same in terms of solid state properties, and one of them is that the band structure is quite different. So one practical difference is that the effective masses are different, and this makes it harder to make quantum dots. And another one is that it turns out, for some reason that I would say I don't completely understand, all of these group 4 elements seem to have more than one minimum in the conduction band. So it means that if you, in gallium arsenide, you have one minimum in the conduction band. So electrons in gallium arsenide essentially behave like free electrons with an effective mass. And if you fill some electrons into the conduction band, there's a Fermi surface, which is just a sphere around the k equals 0, the center of the Brillouin zone. But if you do the same in silicon, you will see that your electrons will fill not at the center of the Brillouin zone, but a bit outside in 6 different points. These are called valleys. And so basically, if you put an electron in a quantum dot, there's not only one state here, but there are 6 in principle. It turns out there are only 2 because in a 2-dimensional structure, some of these are lifted in energy, but you still have this twofold valley degeneracy. So it means if even your free electrons have an additional orbital degree of freedom, some kind of isospin, and this is an additional degree of freedom that can actually mess up our exchange physics. I've told you before that the fact that we only have one level here is very important for exchange coupling, because the Pauli principle sort of makes this statement that you cannot put 2 electrons with the same spin into one orbital. And this will matter. And this is also the case in germanium. It's also the case in graphene. So you have, instead of the 2 spin states, you have 2 spin states and 2 valley states equals 4 states. And instead of this Heisenberg exchange, you will have some more complicated exchange, at least as long as you don't lift this valley degeneracy. So these tau operators here are these valley isospin operators. So I'll come back to that later. So let me see. I think I should wrap up soon. Yeah, let me just go on for 2 minutes, and then I'll just continue here. Of course, I didn't get anywhere near where I wanted to be, but that's okay. I will just continue here in the afternoon. Okay, so this was the materials story, that the nuclear spins were really one major problem for gallium arsenide, and now people have switched to silicon, and we're exploring also other materials. And there are some interesting differences between gallium arsenide and these other semiconductors. The other problem that I alluded to in the beginning was that we need these localized time-dependent magnetic fields to control single spins. And it would be nice to use electric fields for that. And the topic that I will not finish now, but I will talk about in the afternoon then, is ways we were thinking about ways. So basically exchange coupling allows for very fast 2-qubit gates, whereas the 1-qubit gates are slower and harder to implement by this spin resonance. There are some efforts to use electric fields by using spin-orbit coupling. This has also been implemented at Delft. You can also try to use magnetic field gradients or nuclear spins. So basically, these are all efforts to couple the electron spin to an electric dipole and then use electric fields to couple to the dipole. This also leads to increased sensitivity to charge noise. And there's always a kind of engineering problem to come to terms with this. Okay, so I think, so now the next step will be to try to use essentially systems or implementations of spin qubits where you can work only with the exchange coupling. So we'd like to sort of get rid of this or use this as little as possible and basically rely mostly on the exchange coupling. And it turns out for this you need to extend your qubit to be represented by 2 or 3 electron spins. And this is something I will talk about in the next lecture. And so I think I'll close here and just postpone everything else for the afternoon. Maybe there are, if you have a few questions, we can still take some questions.
Thanks. So questions?
The relaxation processes are somehow independent, right? Or even the T1 and T2. So is this justified because you're sure that the noise correlation scales are all somehow independent?
Yeah, so I think that's it. So the question is whether I can really treat relaxation and decoherence independently for the qubits, or there's correlations. And I think as long as the qubits are not coupled, I think this is quite a good approximation. At least for the nuclear spins, they're very local. So every electron spin talks to its own set of nuclear spins, more or less. And for the T1 is mostly due to emission of phonons. I'll get back to that later. And then it depends on the phonon wavelength, essentially. So there could be some correlations. And this is it's a good question because usually when we discuss quantum error correction, we assume that all errors are occurring independently in our error model. And I don't think that's always true. But I think to some approximation, it's probably correct.
Questions? More questions? Yes.
Yeah, this spin-orbit coupling will mean that, so what you will do is with your electric field, so you have your potential here. Imagine you have a harmonic potential with an electron in it, and you apply an oscillating electric field. So the electron will, carry out some oscillatory motion, and by spin-orbit coupling, the state will see in its rest frame an oscillatory effective magnetic field. And of course, if you add to that pure sinusoidal electric field also some noise, then the electron will also a little bit jitter, and then there will also be fluctuation effectively in this effective magnetic field. And that will lead to exactly this T2 dephasing that I've shown you before.
Yeah.
So is always a low voltage situation used for all the operations, or is there any situation where the voltages applied are large?
Okay, so that's something you probably have to ask the experimentalists. I don't even know what exactly you mean by low voltage. So I think the voltages here are usually millivolts that are applied on these gates, but I think you have to also then translate these voltages, energies in the quantum dots. And this is a complicated, basically capacity problem. I mean, you can, essentially you have a vector of voltages and you have a vector of energies, or basically there's a big capacitance matrix in between. And this you can determine. So there's this so-called leverage arm, and this step depends on the structure. So, but I don't know whether that answers your question. It's typically in the millivolt range, I think, but maybe I don't know, if Jason Pedder was here, he could probably answer that much better than me. As long as possible. A millisecond is very good. I mean, we are comparing here with, these operations are fairly fast. So if we have milliseconds, that already means we are in a good shape.
More questions? So if not, let's thank the speaker.